Thank you. Can you see my screen?
Yep.
Okay. So yeah, I'm going to talk about our recent progresses on the completeness of on the universal completeness of ZXW-calculus for arbitrary finite dimensions. This is a joint work with Harney, Razin, Leah, Richie, and finally Bob. Okay, so let's get right into it. So what we have proved is that the ZXW calculus is universally complete for all finite dimensions. And we did that using a unique normal form. We show that every diagram, every ZXW diagram equals 1 in normal form. So let's have a quick overview of what completeness actually means. So we know that a graphical calculus is complete if we have two diagrams that are mathematically equivalent, so their interpretation is the same. Then in a complete calculus, we should be able to show that these two diagrams equal. So we should be able to rewrite, in this case, D1 into D2. And so for the ZX calculus, there is a universal completeness for qubits. And also we have the completeness of the Clifford or stabilizer fragment for prime dimensions. And here what we prove is that the ZXW calculus is universally complete, which is a really general statement for all dimensions, not just primes, but for all dimensions. So this result is quite general. But let's look at how we actually prove this result. So first of all, by map state duality, we only have to consider state diagrams, right? So those diagrams that don't have any inputs. Then what we do is we have this normal form. And so if we know that two diagrams have the same interpretation, then this means that their normal form should also equal. So we transform both of the diagrams to this normal form, and therefore we know how to rewrite D1 into D2 because we go from D1 to the normal form, and from the normal form we go back to the other diagram by reverting the rewrite steps from the normal form to the other diagram. So that's the general idea of a completeness proof that uses normal forms. And in particular, let's discuss how we do this. So first of all, we know that each diagram consists of generators, right? And these generators are composed sequentially and parallelly, right? So we have these layers that we call here A1 and AJ in general. And each of these AJ layers consist of generators parallelly composed. So then what we do is, first of all, we convert the top of the diagram into normal form. So this is only converting generators into their normal form. Then we bend the top of this general diagram so that A2 is now in a state form. Then we transform A2 into normal form. So A2 is again a generator, but these generators are bent into state diagrams. And then we have two diagrams in normal form next to each other, and we transform the tensor product of these two normal forms into a new bigger normal form. And lastly, we have to reduce this partial trace of this normal form into another normal form. And we repeat this step for all of these layers. And in the end, we end up with a normal form. And I have just realized this should be A3 and AK here. So the original diagram. But the top is the thing that's in normal form. So we just simply consume this diagram, translating it into normal form. And in the end, we end up with a normal form. So this is our strategy to translate any diagram into their normal forms. So let's just summarize it up. We need to convert each generator into a normal form. We need to transform the tensor product of two normal forms into another normal form, and then we need to take the we need to convert a partial trace normal form into normal form to prove completeness using this strategy. So these are the three requirements we have. All right. Now, we use the ZXW-calculus. This is a relatively new calculus, but there are already a couple of examples where people used the ZXW-calculus to explore interesting things. For example, Racine, Harney, and Ritchie has a paper on Hamiltonian exponentiation and summation using the ZXW-calculus, and also Harney, Ritchie, and Mark has a paper on how to differentiate and integrate ZX diagrams, and they also analyze its usage in quantum machine learning to detect Brem plateaus. All right, and also one interesting thing is that we have a nice normal form in the ZXW-calculus. So given an arbitrary vector x of dimension d to the power of m, we can represent that vector in the ZXW-calculus. And at this point, it should be a bit unclear what this actually means, but let's explore what actually this means. So first of all, we are working in the Qudit version of the ZXW-calculus, not the qubit. So what are actually qubits? So qubits, in qubits, we have two computational basis states, 0 and 1. We have two options, right? It's like, and in Qudits, we have not just 0 and 1, but we also have 2 and so on until d-1. So we have d computational basis states, and every state can be in the superposition of each of these d states. Then, so we saw this kj on top of the normal form. And these in our calculus are like the pi phases. I think that's the easiest way to understand it. So they can copy, just like in the ZX calculus, they can commute through phases. They are interesting and they are usually easier to work with. And in our case, the interpretation of kj is actually the minus j computational basis state. So this is actually really important. So the interpretation of this kj spider is minus j, and it helps a lot to think about it this way many times. Also, it's worth mentioning that k0 is the empty spider that we also see in the ZX calculus. So then now we know what this top means here. And this is actually just, minus j means d minus j. So we take this basis state modulo d. That's also important. So now k1 means so this means the d-1 computational state. So the very last element is 1 in a big vector, the elements in the vector. So then let's see what this black triangle means. So this is the W node, which is really closely related to the W state, if someone is familiar with that. And what's important for us is how it acts on computational basis states. So if it gets the 0 state in, then it outputs to 0 states, which corresponds to this part in the sum. And then if we input kj, then we will have a sum, a superposition of both kj0 and 0kj. Then this W node can be generalized into to have n legs or any number of legs. And it will be really similar to the two-legged case, but in this case, we will have a huge sum. And in this huge sum, we will have kj in each of the places it can be at. With 0, it behaves the same way, but this is really important. So if this triangle, the W node, has n legs, then we will have a nice superposition of all of the kj's being at every position. So it's really good to sum things up using this W node. So now we see that in this normal form, we have k1 and the W. Then we will have a sum of all k1s at each of these boxes that we will explore a bit later. But first, so we have this sum, and it's a bit too lengthy. So let's just focus on this middle part where we have the xi, so the ith element of this sum. So what I state or claim here is that this node or this part of the superposition is going to correspond to a vector where every element of this vector is 0 except 1, where it's going to be xi. And the position of this element is going to be determined by these multipliers and the values that are in them. But first, let's see what this green box means. So in simple ZX, we have the Z spider. And in this case, this has a single input and a single output, right? And we know that this spider corresponds to Z rotations. This is the general Z rotation gate. And alpha can be any real number. Now the Z box is a bit more general, to say so. Here we don't just have e to the I alpha, but we have any number a that's related to the phase of this Z box. And this a can be any complex number. So in a sense, the Z box is more general, or we can represent the Z spider really easily using the Z box. But we can also represent other things with the Z box. But this is obviously the qubit case, because we have 2 by 2 matrices. In the qubit case, we have d by d matrices, and we don't just have a single complex number, but we have d minus one of these numbers. And this Z box corresponds to a diagonal matrix where each of the elements are part of the phase of the Z box, except the first one, because that's going to be set to 1, strictly set to 1. And we have a really nice and compact way to represent this matrix using a simple sum. What's the trick is that we set A0 to be 1, and then we get this matrix. But this is still just a one input, one output Z box. In general, we have n legs and n plus m legs, right? Inputs and outputs. And just like in the ZX case, with the Z spider, we have these computational basis states m times and n times, corresponding to the number of inputs and outputs. All right. And lastly, one thing that's super useful or makes our life quite easy is this nice notation for the phase of the Z box. So when we represent the phase with a single complex number, we mean that the very last element of this vector is actually that particular number, so X in this case, and everything else is 0. And if we look at the normal form, we actually do use this notation here as well. So these things mean that the last component of that vector is actually the numbers that you can see there. And also something worth noting is that because Z spiders and Z boxes are so closely related, their definition there is that most of the time you can think about them in the same way. And here just as well, they are going to copy through, the basis states will copy through these things. And what we end up with here is this scalar and all of these basis states copied through. But here we only had this K1 here. So K1 is going to be connected to these multipliers. And if we write this thing up, we can see that this actually corresponds to just xi scalar. All right. So then we have another really useful notation for Qudits, which is called the multiplier. So this multiplier is a Z box and an X box. A Z spider and an X spider connected with the number of that many legs as the number indicated in the multiplier. So the weight of the multiplier. It's maybe worth mentioning that in qubits. We have the hop flow, which means that if a Z and an X spider are connected with 2 legs, they are going to disconnect. But in the Qudit case, this is not like this. We need to be connected with D wires in order to disconnect. And so M does make sense as long as it's smaller than D, but if it's bigger than D, we can take it modulo D, and we will have a nice notation for that many legs. Also, we can transpose the multiplier, and then the Z and X spiders flip. And let's see how the multiplier works with just simple basis states. So if we have Kj on top of a multiplier, then it's going to first copy through to each M legs. And then these Kj's, each of them will merge. So we have M times Kj, and that's Kmj. And in our case, J is K1. So this is going to be just the number that's corresponding to the weight of the multiplier in the normal form. So we have this these basis states, which actually corresponds to this cat. So it's these elements times the scalar, and actually this is how we do the normal form, right? We have all of the possible elements in every place of this cat. And we have all the scalars we need, and that's how we can represent any complex vector. It's maybe an easy way to think about it is it's really close of these weights is like the ternary decomposition of a number, and we have d to the power of m numbers. So in case of qubits, this is actually just the binary decomposition of a number, which is something computer scientists must be really familiar with. But here we have d dimensions. So it essentially works the same way, but it can express much more numbers because of the power base is bigger. All right, so this is the normal form. Now let's move on to the rest of the generators of the ZXW-calculus. So obviously we have the Hadamard box, and this matrix may seem a bit hard to understand at first, but it's actually just this sum. So at every row and every column, we have j and k, and we have j times k. So this is the first row. We have omega to the power of 0 times 1, 1 times 1, 2 times 1, r times 1. And this is how we get each of the columns. And also, it's not too important to know this notation. It's only important because of the proof that we need later on. But what you should remember from the Hadamard box is that it's really similar to the qubit case. There will be a tiny flip, but let's talk about that later. We also have the swap and the identity as generators. Nothing special. They work just the way they would work with qubits. We also have the original Z spiders easily represented in the ZXW calculus using the Z box. If we set the phase of the Z box to be e to the power of alpha, where alpha is a vector, then it just represents the green spider. So they are essentially syntactic sugar, but they are really useful in many cases. So in Qudits, the Hadamard dagger is actually not the Hadamard. So the Hadamard is not the Hadamard dagger is not the inverse of the Hadamard, but actually 4 Hadamards does end up as an identity. So we define Hadamard dagger as 3 Hadamards the application of 3 consecutive Hadamards. We have the dualizer, which is a bit of a pain to deal with, but they are part of Qudits. So these dualizers are a structure like this. So this doesn't correspond to the identity as it would with in the qubit case, but it's actually corresponding to flipping the computational basis states. So there are 2 versions so there is this fleximetric version of a calculus we can choose, or we can choose to deal with things in a bit harder way, but we chose this part because it seems easier. Then an interesting thing is that the yellow.
Sorry.
Yeah.
Quick question. So am I right in saying that the dualizer here will be 2 Hadamards in a row, or is that not the case?
Yeah, that's the case. So
right.
in the rule table, we will see a rule that corresponds to the dualizer actually equals. So this thing equals to 2 Hadamards. And also, if we go back to the multiplier, it's actually a dualizer is a multiplier with d-1 wires. So these 3 things actually equal, and they are kind of convenient to work with because of that. Thank you. Yes. So the yellow triangle is an interesting construction that have been used in a couple of instances. And in the ZXW calculus, in this calculus, we actually don't need the yellow triangle. We don't have them in our rule set. It's just syntactic sugar. Sometimes they are useful, but we actually don't really use them now. And lastly, for the notations, we have the V and the M boxes. So these notations are only there for brevity because, as you can see, they are quite big, but they have really nice interactions with some of the generators, as we will see, and they actually are really useful. So the V box is actually a Z box with 0, 0, 1 phase, right? Everything else is 0 before the last element. And then we have the W node connected through all the possible multipliers from D minus 1 to 1. And they are connected to a Z, an X spider. The M is really similar, only that we have an extra 0 multiplier. And then let's see the actual rules of this calculus. So these ones shouldn't be too much of a surprise. This is the ZX part of the rules. Something to note is that because of the way Z boxes are defined, when they fuse together, the phases are actually multiplied element-wise. Unlike with the Z spiders where they are added. We have the identity rule. With the dualizer, the elements of the phase in a Z box just changes, so it reverses. We have the empty diagram. We have the bialgebra between the Z and X spider copy. We have a nice rule that describes how the KJ spider with one leg and so one input and one output interacts with a Z box. Furthermore, we have here the rule with the dualizer that it actually corresponds to 2 Hadamards or a multiplier with -1 weight. So just to go back, this is -1 means D -1. So we have D -1 of these wires between these two nodes. And this rule is, it's almost like the color change rule, but the red spider is not a generator for us. So this is how we define it. And using this rule, we can derive the color change rule. Then we have the ZW part of the rules. So this is really similar to the general ZXW-calculus. Maybe something to note, though, is the WW rule, which is quite interesting. So it's like an algebra between the W and the W node, but for it to work, it has to be connected to a structure like this. So it has to be projected onto this subspace. But this is actually quite useful for us in this way just as well. Then we have the interesting part.
Could you go back?
Yes.
This bialgebra there, because like these other bialgebras, you can interpret as sort of these classical relations. Like for instance, this left one is copying and addition, right? This is saying like
Yes.
addition is like a function of the basis states. What is this WW stating? Like, is it something similar you can interpret?
To be honest, I haven't thought about this in that way. So right now, I'm not going to be able to give you a decent answer, but yes, I will maybe.
Maybe to ask it differently, this W state connected to a W state upside down, like the left-hand side. What is the linear map there?
This one?
Yeah, what's a linear map? Is it a projector or something?
So we have just a second.
Yes.
So we have
I think this part is.
Harney says that it is.
This part is.
That part is. Yeah.
Okay.
Yeah.
Maybe just carry on. We can discuss this later.
Okay, sorry. Yeah. Yeah, let's come back maybe later. Any more questions, actually? Well, if not, let's go on to the ZXW part of the rules, which is maybe the most interesting, because these are the rules that have not yet really been present in previous works. So these two are just nice ways to describe how the W acts on computational basis states. This is the tri-algebra rule, which is actually quite remarkable, because this means that the Z, X, and W generators, when they connect together, they actually have a nice rule. And so the ZXW-calculus is not just it's actually more than the sum of its parts. It has really nice interactions with each of the generators. And yeah, and then we have this rule, which is seems a bit ugly. Well, it is, but it's necessary. Oh, something to mention is that these multipliers, they can be any number from 1 to d minus 1, but they can't be 0, so they can't disconnect. That's important. And the last part of the rule set is, first of all, the Hadamard decomposition. This was a hugely non-trivial rule to derive, and it took a reasonable amount of time. But in the end, this looks now beautiful using the M boxes. So just to go back, the M box was the W node connected with multipliers from d minus 1 to 0, and the V is really similar, but it doesn't have the 0. Then we have a nice interaction with the Z box and the V box. So if we have a if we have a similar structure to the V box, but we also have just the phases of a Z box at the last place, right? This means that everything is 0 except the last element of the phase. Then we can kind of merge these Z boxes into one, and the V box will move up. The V box also can commute through a W node. And lastly, if we put a Z box state on top of a V box, then this V box is going to select the last element of the phase and make it repeat. And if anyone has any questions here.
What's the matrix of V?
Of V?
What's the matrix?
So actually, I can't remember, but that was super important when we did the proof. Can you remember it?
We have not the matrix form, the linear map form.
Yes. Maybe Leah is here. Razin.
I believe it's something like it's in 0 to 0 and everything else to 1. Like it projects all non-zero basis states to 1. Or is that one V or is that one the other one?
I
Is
think
that one V or M?
It
yeah,
looks like the matrix for one column is just a column of ones and the rest is zero.
Hmm. So it's a projector to the non-cat zero subspace.
But
Yeah.
it copies the vector, right, to every other thing.
sorry.
Like it doesn't just project it, like also takes the last element of the
Yes, that's
thing
right.
and then copies it everywhere, so it's not a projector.
Yeah. Yeah, so this V is a really interesting element in the calculus, actually really important. So just a quick reminder, in the beginning of the talk, I mentioned how we prove completeness using the normal form, and to convert any state diagram into normal form, we needed that we can convert generators into their normal form, the tensor product of two diagrams into their normal form, into another normal form, and that the partial traced normal form can be rewritten into another normal form. So we had these three requirements, and I'm just going to show you the lemmas for each of these. The proofs for these will be presented in an upcoming paper, hopefully soon available to the public. But here I'm just going to show you that these things have been proved. So for example, the Z box. If you recall, then the Z box is actually like every J and J basis states with an AI phase or AJ phase. And so this is just what this normal form describes. So each of these connections represent that we have A1 times 1, 1, 1, 1, 1, 1, then we have A2 times 2, 2, 2, 2, 2, 2 as the basis states. And we can prove this. Then we have the W node bent into a state diagram. And this normal form represents the matrix that corresponds to the W node. And we have proved this. Then we have the Hadamard box. Now this was this was the hardest part of the proof, definitely. If you remember, then this is the matrix of the Hadamard gate. So we have ones in the first row. Then we have 1 omega to the power of 1, omega to the power of 2, and so on to d minus 1. Then we have the square of these elements. And so this is what we describe in this normal form. So this is the first column, all the ones. Then we have 1 omega and so on until omega to the power of t minus 1. We have the rth column, and then we have the d minus 1th column. And this thing actually equals the Hadamard box. We have the tensor product of two normal forms. With the given parameters. So we have two normal forms with A and B phases, then the tensor product of their normal form will be just as you would expect with two vectors or two arbitrary states. And lastly, we can take the partial trace of a normal form and we end up with another normal form. But just like with when you do partial trace with matrices, you end up with quite different elements. So here we sum up all those elements where each index is the same, like each connection to everything is the same except S and T, and those places where we do the partial tracing, and everything else is discarded. And this is how it looks like in the end. So just to quickly sum it up again, we have defined the Qudit version of the ZXW-calculus. We proved that this graphical revised system is complete, universally complete for any finite dimensions. So it's this is the very first universal completeness result for a quantum graphical calculus that goes beyond qubits. And yeah, it's a super general result and really exciting. So what we aim to do later is prove the universal completeness of Qudits ZX and ZW-calculus universally. We plan to apply ZXW-calculus, the Qudit version, to photonics. It's really interesting to analyze circuit extraction of ZXW diagrams, because we have this nice tool, we have nice results related to ZXW. And if we could actually work out how to use these results in actual quantum computers, that would be really exciting. And lastly, just looking for more applications for the Qudits ZXW-calculus, or just the qubit version. And that's it. Thank you so much for your attention, and yeah, I'm happy to answer any questions.
Okay, let's start off by thanking our speaker. So my first question is, so I'm guessing that the main obstacle to proving completeness of, say, Qudits ZX without the W is that you have all of these interesting rules which require the interaction of the generators of the W's to the Z's and the X's. And you don't know how to appropriately replace these in such a way that you can keep the form of the proofs. Is that right?
Not entirely. So to prove the completeness of universal Qudits ZX, what we have to do is express the W node and the Z box in Qudits ZX. So it's actually not that hard, but still it's much more complicated than we initially thought. So what we have to do is we have these generators, ZX, we have the Z box, we have the W node, and we have the Hadamard. The Hadamard is already part of Qudits ZX, so we don't have to deal with that. The Z box is kind of closely related, as you can remember. So that's something we need to do. And lastly, we have the W node. So we have to express the W node in Qudits ZX calculus. And if we can do that, then that means that this calculus is complete, or that calculus.
Right, so it's not even so much a problem with the rules, it's just a problem with getting the decompositions in the first place.
That's right.
Okay, thanks.
So you've chosen to make the X spiders the non-flexometric variants, where a single input, single output, phase-free X spider is the identity, instead of being the dualizer, which is the choice you can make if you redefine your X spiders have dualizers on top. Why did you choose not to make this flexometric? Because I think the W spider itself could also be made flexometric in this way, right?
Well, first of all, this work is really closely related to Harney's work, and in Harney's work, all the proofs are proved for the non-flexymetric version, right? So this made it really easy to work with these things. This is just a choice what you want to deal with. You don't want to, if you want to deal with the extra dualizers between the fusions and dealing with the dualizers, or if you want to deal with a non-flexymetric calculus. So our proofs are actually not that long, and if you do take care of not messing up the ordering of the spiders, it's actually not that difficult to work with this non-flexymetric version. So it didn't really give us any drawback in that sense. But I can imagine that also a flexymetric ZXW-calculus would be really interesting. And maybe that's also something we should take a look at.
Yeah, because you do rewrite the normal forms, you just care about states, but when you're bending these wires for X-spiders, you are doing non-trivial things to them.
Yeah. Yeah.
I have a question.
Yeah.
It's not so much about the ZXW calculus in particular, but more about the Qudits, because if you're working over Qudits where like D is not a prime, then like the Hopf algebra induced by the Z and X like monoid and comonoid corresponds to the ring of integers mod D, and you have this non-trivial zero divisor. Did you ever like run into any problems with like trying to divide by stuff? And more broadly, does that shed a light on like what maybe a graphical calculus would be for the phase-free Qudit ZX calculus?
So actually it was really it played out really well, because so especially with these multipliers, having a multiplicative inverse would be good, because then two multipliers could cancel out each other. But this is not the case. Only for -1, the dualizer is the case, and only in prime dimensions. But somehow it ended up working out quite well.
So you just avoided dividing by things, or
yes,
you like take some other sophisticated approach? You just avoided doing any division?
It didn't really try to avoid it, just happened that it played out well in the underlying structure. We didn't need it. So yeah, that's it from our side. Maybe someone else wants to add something.
Also, I think you can easily, if you drop off the Hadamard and Hadamard diagram and define the pink spider, then you can easily generalize all of these results to the commutative semi-rings.
So carrying on from the question from Cole, if you have a dimension that is a prime, can some of your rewrite rules be derived, like these really complicated ones involving the Hadamard stuff? Because you can imagine that for prime dimensions, like stuff just works more nicely and you can derive more things.
Yeah, actually, then you would be able to do like to have more rules for prime cases.
Yeah, and for example, then I think in the prime cases, the multipliers is is a unity, right? It's invertible.
Yes, yeah. So in prime cases, when you have two multipliers facing each other the other ways, so either these arrows looking at each other or facing the other way around, that's going to equal the identity. Well, in non-prime case, that's not necessarily the case. So in general, this is not true here.
Yeah, but so some of your more complicated axioms that you needed, can those be derived in the prime case? Like these ones involving the V and M matrices, for instance.
Or what was the question?
Like,
For?
can any of these rules be derived if you have prime dimension? Do you notice that
These
you
rules.
don't have to assume them as axioms?
Yeah, as in like, can you get a smaller set of axioms out?
Yeah.
That's a super interesting question. Maybe the case. So we actually haven't really considered minimality. We didn't really pursue it because it was already really complicated, and that could be a really good point. Yeah, that this could be made much more minimal in a prime dimension. Yeah,
Another point that should be made, because it's the same for a normal ZX calculus, is that for a long time, despite not having a complete set of rules, for all practical purposes, everything could be computed. So you don't always use all the rules. And it's possible, and the same is going to happen here too, that some of these ugly rules, you just will never use them. They're just sitting there. It's been the case, it's been the practice with usual ZX calculus too.
Actually, I have a question that's about this ugly rule, this H rule. So I recently realized that we can use an Euler decomposition for H, actually not just in prime dimensions, but in any odd dimensions. I don't really know what it looks like for even dimensions, because the form for the odd dimensions has this multiplicative inverse of 2 mod d inside it, but we can do an Euler decomposition for Hadamard in odd dimensions, which does imply for the odd dimensions we probably could simplify this more into that form. But because it's kind of dependent on the specific value of d for any general d, I'm not sure how much more we can simplify, and if that's what a route to be, if that's something that we would want to do.
Any more questions? Or yeah.
Okay, if there aren't any more questions, then I think we should thank our speaker again. And to bookend the talk with another advertisement, if you have stuff you want to talk about that is ZX related, even if it's not finished, please let us know. Thank you.
Thank you again. Bye.